Central limit theorem, chapter 7. Let x be a random variable with mean mu and standard deviation sigma. Then for sample size n greater than 30, whether or not x is normally distributed, the sample mean x bar is approximately normal with mean mu and standard deviation sigma over square root of n. And the standard n greater than 30 is arbitrary. Some books use n greater than or equal to 30. Generally, the bigger the sample, the closer it is going to be to the mean will be to a normal random variable. There's two special cases. If x itself is normal, then the conclusion are true even for small samples, even regardless of the sample size. And for a second special case, for sample size n and population proportion p, if n times p is at least 5 and n times 1 minus p is at least 5, then the sample proportion p hat is approximately normal with mean p and standard deviation square root of p times 1 minus p over n. And again, the standard of np and n times 1 minus p being at least 5 is arbitrary. Some books use 10. Generally, the bigger those quantities are, the closer it will be to a normal random variable. So here's some examples that I think will help illustrate this theorem. Example 1, suppose that lung capacity has population mean 3.1 liters with population standard deviation sigma 0.5 liters. Suppose that lung capacity was measured in a sample of n equal 1,000 patients. What is the probability that sample mean is less than 3 liters? We are not told whether lung capacity is normal, so we need to check the sample size to make sure it's at least greater than 30, and yes it is, and it's 1,000, which is greater than 30. The second step, the mean of x bar is 3.1 liters, the same as the population mean mu. That's part of the central limit theorem. And the standard deviation of x bar is the original standard deviation divided by the square root of n. So this is going to be original standard deviation is 0.5, and n is 1,000. So square root of 0.5 divided by square root of 1,000. So that's going to be 0.5 divided by second square root 1,000 equals, I get 0.015 something. Okay, so I'm going to store that in memory. Just do enter, and because then we can use it for subsequent calculations. So if we want to know the probability that the sample mean is less than 3, then we can compute the z-score and then look it up in the z-table. So we want the probability that z is less than 3 minus 3.1 divided by the standard deviation, and so that's going to be do 3 minus 3.1 equals, and divided by the second recall equals, and I get about negative 6.32. Z is less than negative 6.32. Okay, so so that's actually lower than anything in our table. Actually, our table is only has the positive z-scores in it, but this is the same as 1 minus the probability that 0 is less than z is less than 6.32, and this is bigger than anything in our table, so it's going to be if 1 minus the biggest number of our table is going to be 1 minus 0.4998 equal 0.0002. So it'll even be less than that because that's actually off the table. So so this is would be quite unusual to get a sample mean that was that small. Okay, so second example. In 1876, actually this should be 0.5, 0.5 minus the table. 5 minus the table. Okay. 1876, although Samuel Tilden lost the election for U.S. President to Ruther B. Hayes in the Electoral College, Tilden actually received 51% or a majority of the popular vote. And that has happened several times in more recent years too, where the candidates receiving the most votes lost the vote in the Electoral College. Suppose that just prior to the election, a random sample of n equal 1,000 voters had been taken. What is the probability that less than half of the voters in the sample favored Tilden? So this is the second special case of the central limit theorem. And we want to check that n times p has to be at least 5. Well, n is 1,000. 1,000 times 0.51 is 510, which is at least 5. That's a yes. N times 1 minus p. Well, 1 minus 0.51 is 0.49. 1,000 times 0.49 is 490, also bigger than 5. The mean is going to be 0.51, the same as the population proportion. The mean of the expected value of x bar is the same. The mean of x bar, same as the population proportion, p. And the standard deviation is given by this formula, square root of p times 1 minus p over n. So it's square root of 0.51. 1 minus 0.51 is 0.49. Divided by the sample size, which is 1,000. Okay, so to do second square root and 0.51 minus 0.49 divided by 1,000. And the calculator, if you push equals, it automatically closes parentheses, so you don't really have to bother with closing the parentheses. I get 0.7. I know that seems a little big. I did. Let me try it again. Second square root 0.51 times 0.49 divided by 1,000. Okay, that seems right now. That's 0.015 something. 0.015808 226. Okay, so I'm going to store that in memory. Sto equals, and then the next step, we want the probability that p hat is less than 5. So we're going to convert that into a z-score by subtracting the mean and dividing by the standard deviation. So 0.5 minus 0.51 divided by 0.015808 so it's 0.5 minus 0.51 equals and then divide by second recall equals. I get negative 0.63. Probability of z less than negative 0.63. And again, our table is based on only has the positive z-scores, so we can we can write this as 0.5 minus the probability of 0 less than z less than 0.63. And that comes out to be 0.2643, or approximately 0.26. So there would be a 26% chance. Am I frozen here? I don't think I'm frozen. There, I'm unfrozen. So there's a 26% chance that less than half the voters in sample would have favored Tilden. We could also do, there's another way of doing this using normal approximation. It's it's related to the central limit theorem, but it's not directly following the central limit theorem. So let x be the number of voters in the sample favoring Tilden. Then x is binomial with n equal 1000, p equal 0.51, and q would be 1 minus p, which is 1 minus 0.51 is 0.49. And then we want to check that n times p is at least 5, and n times q is at least 5, and those are both yes. The mean of x is n times p. So it's 1000 times 0.51, which is 510. So it's related to the binomial, but it's it's related to the probability for a proportion, but instead of a proportion here, we're going to get x is equal to a number of voters in this case. So the mean of x is 510 voters, and the standard deviation, square root of n times p times q, comes out to be 15.8 some voters. And then, so the probability that p hat is less than 0.5 is the same probability of x is less than 0.5 times 1000. So if x is less than 500, then the proportion of voters will be less than 0.5. Oftentimes people will do what's called a continuity correction by adding, subtracting 0.5. Because it's not always necessary to do that, but sometimes it'll give you a more precise answer. So the probability, we're going to say that x is less than 500 if x is less than 49.5. That's a probability continuity correction. And then convert it into z-score by subtracting the mean divided by the standard deviation, and we get the probability of z is less than negative 0.66, and then using the table, it comes out to be about a 25% chance. So it's similar to what we had before. It's before we had 26% chance with the other method, but it's a similar result. There may have been a rounding difference. The continuity correction is not always used. You don't always need to subtract 0.5 because usually for for large, if the sample size is large, the continuity correction is not going to make a big difference in the final answer. The sample proportion is related to the binomial by this formula here. It's binomial divided by n gives you the sample proportion. And that concludes this presentation.